Hello, welcome to the next lecture in the NPTEL course on Haskell programming. Today we are going to look at a new concept, namely input-output. So far we have written Haskell programs which compute some value, so mostly these are functions, and the way we have executed them is to load the programs in GHCI and enter some expression in GHCI. It will produce a result, right? So till now a program is just a bunch of functions. A function of type A arrow B produces a result of type B on an argument of type A. Okay, so you have arguments, you have results, you have functions that produce some result on different arguments. So the programs are run in GHCI. Rather than saying that the programs are run in GHCI, you would write expressions to GHCI and GHCI would evaluate the expressions. Okay, program would be would have function definitions. F of x, y equals something, maybe multiple lines. G of z equals something, multiple cases, multiple lines, guarded definitions, etc. So this is what you would write your program in some editor, VS Code. In GHCI, you would write expressions. F of 520, G of list 1, 2, 3, etc. And GHCI will execute the program, or rather, as we saw last time, it will treat the program as defining a bunch of rewrite rules. It will rewrite the expression according to the rules. Okay, so rewrite according to rules given by the program. And of course the built-in rules. Okay, and it will produce an answer. This has been the standard interaction so far with Haskell programs for us. Okay. Yeah, so GHCI automatically displays the result on the screen, provided it can be shown. Of course, if the result is a function, then GHCI will complain saying that the function is not showable. Okay, we looked at the type classes show and other type classes in previous lectures. Now, this is not how you would normally operate with programs, right? So, in most programming languages, there is a mode in which you will Python, say you would write a Python program, you would start a Python REPL, and then you would load this program and maybe evaluate certain expressions. But there are also ways in which you can execute programs outside of the Python interactive shell. Okay, so GHCI is what you may call an interactive shell. Or a REPL for Haskell. Yeah, rather there are many situations in which you want to just execute programs directly. If you are building a product for some other client to use, then you wouldn't ask the client to load up GHCI and load your programs. Rather, you would compile your programs and you would send a binary, compile to binaries, as it's called, and then you would send the binary, and the client is supposed to execute the binary without worrying about whether the client has Haskell installed even. Okay, because once it's compiled to binary, it should be executable on any program that if you have compiled your program for a specific architecture, then you should be able to run this program on that architecture. The binary you should be able to run the binary on that architecture. Okay, good. So far it's fine, but you would like to execute programs outside GHCI. This is just a requirement of the real world. And more importantly, so far the way we have written programs, there is no user interaction so far. Right, this is important. You write a program, the program is supposed to compute some values for some arguments. You go to GHCA, you supply various arguments, it will produce the corresponding result. You run, you provide various expressions to GHCA to evaluate, and when you get bored, you get out. Or when you've gotten some result that you would like, you then just quit the GHCA session and that's it. Okay. So there is no way to say that, oh, this program, let the program run, and then the program should ask the user for an input. Based on what input the user gives, the program should behave either in one way or in another, and then maybe ask for further inputs from the user, okay, and then produce results accordingly. Okay, so this is how normal programs work. Okay, it is not that you provide the arguments once at the beginning and then there is no interaction with the user at all. Okay, whereas right now the user, we are the users, we use the program by providing expressions to GHCA. Expressions are of the form F5, 12, etc. that I showed just a little bit ago. That is like providing some user input, but it's happening only once and it's happening at the very beginning. Okay, and there is no more interaction with the users. Okay. User interaction is important because you might want to say, oh, you ask the user to enter something, the user enters something and the program does based on what the user enters. Then it shows the user some value, and based on the value the user decides what is the next input to enter. Okay, so this is important. So you would like to accept user inputs midway through a program execution, and you print output, error messages or whatever, diagnostics, some various things on the screen or to a file, or maybe to some to produce some graphics on the screen, whatever. Yeah. So this is what we would like, and Haskell allows you a mechanism for that, right? And we can actually write standalone programs in Haskell. Okay, and for standalone programs, you must provide a function called main. Okay, right? Execution of a standalone of a Haskell program starts with the function main if you are trying to execute it outside of GHCA. Inside GHCA, of course, there is no notion of executing a function. You give a expression to GHCA, it will evaluate it based on your program. Of course, you can also give main as a function to GHCA to evaluate, as we will see. But if you want to evaluate, execute a function, a program outside GHCA, then the program should have a main, otherwise you will get an error. Every standalone program Haskell program must have a main function. Here is the first program for us. Okay, this is the first compilable Haskell program. It has a main, and you are saying put string hello world and a new line character. This character is called the new line. That will print a new line on your screen. Okay, put string is just saying display the string on the screen. Or any output device, which could also be a file, as we will see later. Okay, so this is our first compilable Haskell program, and rather than just talk about it, we should actually now try to write this program, compile it and see how it runs. Okay, but before I do that, we will just quickly look at how you get to compile and execute such a program. You save this file into a file named, in our case we will name it hw.hs. HW stands for hello world. From the 1970s or so, it has become a tradition that one of the first programs you would write is a hello world program, just to test that you have installed the programming system correctly on your machine. But in Haskell, hello world comes pretty late because the usual mode of interaction with Haskell is to write functions and then evaluate expressions in GHCI. Okay, but when you actually try to come to standalone Haskell programs, we again go back to this hello world, okay, as the standard template kind of program that we would want to write first. Okay, now let me switch to GHCI and I will show you what this exact procedure is. The exact procedure is that you will save this file into hw.hs and then you will use the command ghc and file name. This will actually compile it and it will produce some extra files hw.hi, hw.o and hw with execute permissions. Okay, this is important, which means that this is a runnable program. This program can be run, or this file contains a runnable program, let's say. Okay. Okay. So, and then you run the executable HW by using the command /HW. This is on Unix and Mac. On Windows, it's slightly different. Even I have to figure out how exactly it happens in Windows, which we'll see right now. Okay. Let us now create a new program.hello.hs. I seem to have one here from long ago. Yeah. So rather than just saying hello world, I am just saying something like this. Main equals. So in fact, I should remove all this. I can create a new program now, just a much simpler one than this, hw.hs. Okay, and here I just say main equals okay. I have written this program. Let me try to run this program in a terminal. Here is a new terminal. Let me do ls. I have hw.hs. As you can see here, there is hw.hs. Let me do ghc. Okay, now it is compiling. Yeah, I don't know why it is taking so long on this machine, but typically on your machine it should be much quicker. And as you notice, it is not producing something called just hw, but hw.exe. Okay, on Windows machines, you will see that it produces hw.exe. Let me try to see all the files that have been generated. Yeah, hw.o, hw.hi, hw.exe. These are the new things that have been generated. And let me try to execute this. Yes, you see that it prints hello world. Okay, so that's nice. So you have actually managed to write a program, compile it and run it from the terminal rather than from inside GHCI. Now notice that because we put the new line character, there is a line after hello world and after that your prompt is coming back again. But if I did not have that, if I did not have this, and if I repeat the same steps, okay, so here it doesn't seem to make a difference, it's still putting a new line, but there are situations where the backslash n will definitely produce a new line, and without the backslash n you won't have a new line. Okay, we will see examples of this later. It depends on your system. On a Mac, for instance, if I do not have the backslash n, if I don't have the backslash n, so the prompt will come right after the hello world on the same line. Okay, so that's the difference. Okay, so let me revert the backslash n here. Okay, good. So let me get back to the slides. I'll come back to demos a few slides later. Let us just anyway make a note saying that okay, remember you have to execute this in the PowerShell, okay, or one of some whatever terminal emulators that the Windows provides you. On Unix, on Mac OS, of course, you should start the terminal and work with that for all this. Okay. Okay, let's move on. We've been using the words GHC and GHCI. GHC stands for Glasgow Haskell Compiler. Okay. GHCI is the interactive version of the compiler, or you might say that it is the interpreter. Okay, interpreter, playground, REPL, these are all words that you can use, words that you can find to describe GHCI. Okay, so you can think of GHCI as a place where, as a playground where you can test your programs. You write your programs, you immediately test your programs by providing various arguments to your program and asking GHCI to evaluate it. Once you are convinced that your program works correctly, then you can go back and add a main appropriately and then make it a standalone program. Okay, we will see examples of this soon. Yeah, so as I mentioned before, software intended for use by others is always written as a standalone program. You compile it using GHCI and you ship it to the other person, and they will run it on their machine. Okay, provided you have compiled it for the correct hardware platform. So there are some advantages to using GHCI over GHCI. Compiled versions of programs run much faster and use much less memory compared to running them in GHCI. But we are writing mostly toy programs, so we wouldn't appreciate the difference so much. If you once you ramp it up to some industrial level programs, then definitely you should always it will almost always be run as a standalone program rather than inside GHCI. So you can actually learn more about GHC and compiler options by just typing GHC -- help on the terminal. You will get to see lots and lots of options and much more detail about GHC. You can say GHC -- show options to know about all the options, and that's a very huge list. Even I don't know more than a tiny fraction of these options. So the GHC manual can be consulted. You can easily search for it on the internet, and that's a comprehensive document both about GHC and GHCI. It's not about Haskell programming per se, but about actually using GHC. Okay, various options and so on. Lots of options related to optimization, for instance. So we'll try to provide these slides, and this is a clickable URL, and you will see that if you click on this URL, you will be able to access the GHC manual. Let's get back to our hello world program. I said that okay, you would write put string hello world with a \n. Put string str prints the string str on the screen. Okay, that's its behavior. Whereas, okay, so okay, let's dig a little deeper into put string. Clearly, put string is of type string arrow b because it takes a string as argument. Okay, so this is argument. Okay, string arrow something. What is that something? Okay, let's try to figure out. So once you put a string on the screen, that's it, right? So technically speaking, Haskell should have all functions in Haskell should have type, some argument type, arrow, return type. In fact, you can skip the argument type. You can have a Haskell function with 0 arguments. So there will only be the return type, but you can never ever skip the return type. Okay, you can have. But you can never have a function without a return type. Right, return type means some object is returned, but what is the object that is being returned here? Okay, with put string, there are two things that are happening with put string. Rather than saying returned, I will say a value is produced. What value? We'll come to that. But also something is printed on screen. Notice that this is different from all other functions we have seen so far. If for instance you say factorial 5, of course something is printed on the screen, but that is only because you ran it in GHCI. Because GHCI, all expressions and passed to a specific function called print, which is why something is printed on the screen. But as far as GHCI is concerned, if you give a function, the function should be evaluated. That's it. It should produce a value. That is all the function worries about. The function f that you wrote only concentrates on producing the value. not printing. Whereas put string is actually printing it on the screen. Okay, so there are two things that are happening. Something is printed on the screen and a value is produced, but this value is not used at all. It is in fact what you may call a dummy value, right? Because when you are writing something on the screen, what kind of value do you want to produce? You are saying that you are producing a value only because all Haskell functions require a return type, okay? And here the return type is a dummy type which has a dummy value, okay? So that type is called unit, okay, a dummy type. With a dummy value. Okay, it's called unit and it's written with an open parenthesis and the closed parenthesis. Recall that this is just a generalization. So if you can write 1, you can write 1, 2, you can write 1, 2, 3. These are pairs. This is a pair, that's a triple. This is a quadruple. Similarly, if you want, you could write something like this, even though I don't think Haskell allows this, but most importantly, you can generalize this and have a open parenthesis and close parenthesis without anything in between, without anything inside it, and you may call this a 1 tuple if you want, and call this a 0 tuple. Okay, 0 tuple, 1 tuple, 2 tuples which are called pairs, 3 tuples which are called triples, 4 tuples which are called quadruples, quintuples, but after that sometimes you just call 5 tuples, 6 tuples, etc. Okay, those all can be values. So the empty tuple is also a value. Okay, that's both the type and the value, because you would say int and its value will be 2 comma true, etc. Right, this is the value and that's the type. When it comes to so notice that you use the same notation for both, except that in the type you will write types inside the parenthesis, in the values you will write values inside the parenthesis. So if you extend it to the unit type, then you will write this for the value and that same thing for the type also. Okay, that's it. So the unit type is a type which consists of exactly one value. So you can think that that is why it is called the unit type, because it has exactly one value, and that value is also denoted the same way with an open parenthesis and a closed parenthesis. Okay, so I can test this by, right, in a while I will test this by going to GHCI and checking what the type of unit is. Okay. Okay, so the unit type consists of a single value which is also denoted by the same open parenthesis, close parenthesis. The value is also called unit. You can use it to model a dummy value of a dummy type. Okay, fine. So now let's get back to the question, what is the type of put string? Is string arrow unit the type of put string? It could be, but the point is we are now, this ignores one other aspect of string. Recall that I said two things happens with put string. Put string produces but also writes something to the screen. Such a thing is called a side effect. And side effect are ubiquitous in other programming languages. You write any program in Java or Python or C or one of these things, the program could ostensibly be something that computes some number value from a number argument, but in the course of computing it, it could read a file, it could print something to the screen, it could read a value from the user, etc., etc. Okay, so side effects are sort of uncontrolled in other languages. We will see that in Haskell, Haskell tries to control the side effects, but For the moment, our question is what is the type of put string? It can't just be string arrow unit because that ignores the fact that put string is producing a side effect. So you need to take that into account. Yeah, so put string does not return the value empty unit, or rather we don't use that value, and we are not accounting for the side effect of printing something on screen. So if you go to GHCI and check for the type of put string, you will see that it's of type string arrow IO unit. Okay, so this is special to Haskell. Handling of side effects. Right? Any user interaction is also a side effect because the program talks to the user, reads some input provided by the user, writes something on screen for the user to read, etc. These are all side effects, and Haskell carefully demarcates those programs that have side effect from those programs that do not have side effect by tagging all side effectful programs with IO. Okay, you can think of IO as a tag for values with side effect, values, functions with side effect. Okay, good. So let's get back to this, but we can go to GHCI and try to test these types, etc. Okay, so here I have a GHCI session running. Here is a GHCI session running, and I can ask what is the type of unit. Right, it says unit is of type unit. Okay, so this is what I meant. The value is of type, the value is denoted this, the type is also denoted the same way, but it will never be a confusion as to when you are referring to the value and when you are referring to the type. Okay, now let's try to say put string hello world here. Right, now you see there is hello world which is printed and this GHCI prompt appears right after it. Okay, that is because I didn't put a new line. So if I put a new line, now you will see that it's fine. Okay, you have printed hello world and after a new line you are printing GHCI. Okay, \n stands for new line. Okay, okay. So what is the type of put string? Yeah, as you can see, string arrow IO unit. What is the type of put string? Hello. Because you're providing an argument of type string to put string, it's a value and the value should just be IO unit, and you will see that it says put string hello and its type is IO unit. Okay, I hope that makes it clear. Now rather than saying put string and then whatever string followed by a \n, you can always say put string line. Okay, put string line will automatically add a new line to the end of the string. See, unlike put string which printed that hello world and then immediately printed the prompt as you see here, right? Put string line prints this hello world and then puts a new line and after that only the prompt appears. Okay, good. So this is just a very basic introduction to this. This is one of the first input output actions that we have done. We just printed out something on the screen. Okay, this is a good first step, but there is a lot more to do. Let's get back to the slides. Okay, we saw IO unit, put string is of type string arrow IO unit. What is IOA. Okay, IO is just a type constructor. Okay, nothing mysterious about it. It is just like maybe or list formation or whatever, right? For instance, if A is a type, maybe A and list A are types. What are the values of type maybe A? Just X, where X is of type A, and what is the type of another value would be nothing. What are the values of type list A? Anything, X1, X2, X3, each Xi is of type A, right? So we have seen this. Okay, you have from a given type you can produce other types, and the values of that other type, the container type, will have a certain structure. Okay, if it's maybe A, then values are of this type, values are all of this kind. If it's list A, then values are all of this kind. The values of type list A are related to values of type A, right? Similarly for values of type maybe A. Okay. Likewise, IOA is a type whenever A is a type. So you can actually have IO int, IO string, IO bool, etc., etc. What are all these? These are all input output actions, something they do some interaction with the user. Let's say the simplest case would be that they print something on the this thing, or they read something, or they do something, some interaction with the real world, and they produce a value. Okay, of course we also saw IO unit. IO unit produces a value which is a dummy value. Okay, just because every function should produce a value, it is producing a value. Okay, not that that's a useful value. But IO int, IO string, IO bool, etc. produce useful values. The simplest thing would be to examples of such functions would be to read an integer from the user. Read a string input from the user. Similarly, read a Boolean value. Okay. Okay. So IOA is a type whenever A is a type. So we know that values of type maybe have this structure. It's either nothing, or it will be of the form just X, where X is of type A. Nothing and just are called value constructors. Okay. Similarly, for list formation, you have two value constructors, one which is this, you may call it nil, and another which is colon, which you may call cons. Okay. These are value constructors for lists, let us say. Value or data constructors. Okay, you have type constructors, data constructors, or value constructors, and you know explicitly what the value constructors are for maybe. Yeah, similarly you can have type either AB, that's a type constructor. So this either is a type constructor. Value constructors are left of type A arrow either AB, or right of type B arrow Okay, so you have value constructors like this. But unlike for these types, IO, which is also a type constructor, does not allow the programmer to access the value constructors. Okay, so the internal structure as well as the value constructors or IO are not visible to the user. Okay, this is important. That is the main difference between IO and type constructors like maybe either, etc. Yeah, so one can understand IO roughly as follows. IO itself is shorthand for real world arrow, the pair real world comma A. So what this means is that IO takes a state of the real world as input and produces a different state of the real world along with a value of type A. Okay. So an object of type IOA is a function that takes the current state of the real world as input, produces a new state of the real world and a value of type A as output. Okay. In other words, IO objects of type IOA consist of two things: a value of type A that can be extracted, okay, this is important, and some side effect, some change that has been caused to the real world. Okay. And now extending this, A arrow IOB should be thought of as a function. Let's write its description here. Takes a value of type A and produces a function, really, right, that takes a state of the real world as argument and produces a change state plus a value of type B. Okay. So you can think of A arrow IOB as this. Okay. And earlier we had string arrow IO unit. Notice that the unit is a dummy value, so you can ignore the unit. So string arrow IO unit means that it is a function that takes a string as input and produces an action, let us say, and this action is something that takes a state of the real world as input and produces a new state of the real world. Put string, what is the new state produced by put string? So think of the real world as containing lots of things, including the computer's memory, the whatever is on the screen output that has been produced so far, let us say. The new world, that is the state of the current world. The new world is one where one extra line of output has been produced to the screen. Okay, so it's as simple as that. Okay, but it's still a change in the state of the world. Okay, because something about the real world has changed. Earlier, me as a user did not see a line on the screen. Now I am seeing a new line. Okay. Okay. So technically an object of type IOA is not a function, but I mentioned the word action just now. So it's an action of return type IOA. An IO action produces a side effect when its value is extracted. Okay, you type to extract the unit value, let us say, at that point it will actually produce its side effect of changing the state of the real world. Okay, so this is just a technicality, you can ignore this. As far as we are concerned, it's just you have normal functions of type AROB, you have IO functions of type ARO IOB. Okay, that's all you need to worry about. So just as we compose functions, we can chain actions. Okay, this is the next thing. So if I have, what does composing function mean? If I have f of type A arrow B and g of type B arrow C, then composition f dot g is nothing but lambda x of g applied on f applied on x. Okay, right? You first apply f and then you apply g on the result. That is composing functions. Similarly, you want to chain actions, but remember, chaining action means that originally the first action has produced a side effect, or in other words, the first action took a state of the real world and produced a changed state of the real world. The second action should take the changed state and add its own new change to the state. Okay, so that is what you mean by composing chaining actions. We will see how to chain actions in a bit. So pure functions or actions can be embedded inside actions. So inside actions you can have, so let's write this. What is a pure function? It's just a function that does not have IO in its type. For the moment, let us take this as the definition. So inside actions you can have actions, you can have pure functions. Inside pure functions, you can only have pure functions, you cannot have actions. Okay. The moment you embed an action inside a larger object, that a function or some such, that also becomes an action. Okay. It cannot remain a pure function any longer.